Today, I'll be presenting on the effect of the social contagion in solar panel adoption through a process modeled with commuter and socioeconomic networks with a network science approach. My name is Aritra Ray, and I'm a junior at Princeton High School. During this presentation, I will first be going over some motivations and background for this project, as well as then the modeling methodology, data collection, and then the key findings and discussion, as well as the policy recommendations for this work. So currently, we are undergoing a climate crisis where widespread residential solar adoption is critical for reducing the total greenhouse gas emissions. So residential solar plays a really important part in the fight against climate change and in sustainability measures as a whole. But the solar panel market is changing. The solar panel market is projected to grow to 436 billion by 2032, yet US installations dropped 31% in 2024, which represents the first market contraction since 2017. And one of the most significant barriers to adoption is high customer acquisition costs. That is, the cost of acquiring one customer is quite high, and thus pointing to the importance of non-economic behavioral drivers of adopting solar panels, which is exactly what this study aims to better understand. And in terms of previous literature, foundational studies, specifically Bollinger and Gillingham in 2012, prove that installation increases the probability of nearby adoption by 0.878 percentage points. That is, the peer effects of installation visibility can cause true changes in behavior. But there are certain key debates or unresolved points in these previous studies, specifically the visibility of these solar panels, that is, does seeing a neighbor's solar panel drive adoption, and moreover the effects of homophily. Do we adopt because we share socioeconomic traits with other adopters, that is, income, education, and race? And these factors are what this study aims to better understand, as well as a previous study by the Lawrence Berkeley National Lab found that the even though there are peer effects, the authors explicitly suggested further research into the nature of these social interactions. So our study tries to understand and disentangle the mechanisms by directly comparing socioeconomic similarity with information flow in these peer effects and understanding the mechanism of the social contagion and the mechanism of the peer effect. So the key question is, what is the mechanism of the social contagion for solar panel adoption, information flow, or socioeconomic similarity? And we hypothesized that if the principle of homophily as opposed to information flow was the dominant mechanism in social contagion for solar adoption, then a network science model built on socioeconomic similarity would produce communities with more uniform solar adoption rates and correlate more strongly with real-world adoption data. That is, if these communities have similar socioeconomic characteristics, they would be more likely to have less deviation within the community, which would point to the strength of a homophily-based model. To test this hypothesis, we strongly relied on the deep solar dataset from Stanford University researchers, Yu et al. In 2018. So this dataset provided census tract level solar panel counts and as well as demographic and socioeconomic variables. So this deep solar dataset provided a lot of detailed data used to define peer groups and geographic proximity because it was a very detailed dataset. We also used the ACS 5-year commuting flows data from the U.S. Census Bureau, which contained county-to-county worker movement or commuter movement. And this, which is a key part of this project, was utilized as a proxy for social and informational linkages. That is, by using a change in by using commuter flows, we were able to model information flowing between communities, and this was a key proxy for this study. And this data was aggregated to a tract level to US counties from the tract level data to make sure that these data sets were comparable. But again, going back to the ACS survey, by modeling the number of workers commuting between US counties, this served as a direct proxy for information flow and social interaction. This was followed up by some exploratory data analysis, and here you have the correlation matrix of key socioeconomic factors and solar adoption, which shows very clear bivariate weakness. That is, there's no one clear socioeconomic indicator that really predicts, a lack of solar adoption or a increase in solar adoption. You can see here even the strongest ones are 0.24 or 0.23, which was average household income. But the fact that there's no dominant linear predictor motivated the use of a multidimensional information theoretic approach for this problem. And this is where network science is uniquely capable. So network science provides the optimal framework for modeling multidimensional similarities and interaction pathways as shown by Kirkley 2020. This methodological framework proposed an information theoretic network approach to analyze spatial socioeconomic correlations, and our study demonstrated that network science provides a quantitative framework for modeling these multidimensional similarities between geographic regions. And so Kirkley's work was the methodological inspiration for the construction of the socioeconomic similarity network, which I will go into more depth later on. But it represented three distinct undirected networks, with the nodes being US counties, the edges being the mechanism of connection, and the weights representing the strength of this proposed mechanism. Moving on to the socioeconomic network, which was the first network created. This network models homophily. It uses geographic centroids with a 1 degree latitude threshold, which was about 69 miles. And to calculate the weights, we used a Jensen-Shannon divergence index across 6 normalized feature sets, which you can see here. These are socioeconomic and demographic factors like education level, race, occupation, poverty, home ownership, and voting patterns. And these JSD scores were averaged into a dissimilarity matrix and then transformed via an exponential decay function, which you can see here. And this was critical for normalizing these weights. Then the commuter network was again used to model information flow and the interaction of people in a geographic sense. So the edges were sourced directly from the ACS commuting flows, but to reduce noise, commuter links below the 60th percentile of all national flows were pruned because otherwise there are nearly too many and it causes noise in the network. And edge weights were log normalized to stabilize high variance in national commuter volume, for example, in cities versus rural areas, but applying a log normalization helped address this problem. And this is just an example of what the commuter network looks like visualized. So this is for the state of Massachusetts. This is the partial network. So each of these nodes represents a county in Massachusetts. The blue nodes represent Massachusetts counties, but of course, at least in the United States, much daily commute occurs between states. So for example, Rhode Island, New Hampshire, Connecticut, New York, Vermont, these are all counties outside of Massachusetts where Massachusetts residents commute to on a daily basis. So you can see the relative strengths of the connections based on how thick these edges are. So there's a lot of self-commute within a county, so this represents a self-loop in the network, and then thinner connections between other counties. But again, this was a visualization of those networks. So to summarize, there were 3 network models used: a socioeconomic similarity network to model homophily, the commuter network, which was the information flow model with the ACS commuter data as a proxy. And finally, we also made a state level network, which was a sort of baseline. It was all fully connected components, within a state to test the influence of state level policy. How important was state level policy for understanding solar adoption patterns? The first phase of analysis, and there were two phases of analysis. The first phase of analysis was a static analysis with the Louvain community clustering algorithm. So this heuristic applied to identify distinct non-overlapping communities, as shown in the work of Blondel et al. 2008. So this community clustering algorithm allowed us to understand the distinct networks between distinct communities within these networks, and to compare the strength per se, or the how homogeneous these communities were, we used the weighted average intra-cluster standard deviation. So intra-cluster meaning within one cluster, and then weighted average based on the number of counties and the deviation within these. So a lower standard deviation indicates a higher cluster homogeneity, proving that the network topology accurately maps real-world behavior clusters. Because if there's a lower standard deviation between all of the solar adoption rates within a cluster, that means this is truly a cluster even in real life. So it sort of measures the strength and how accurate this clustering is by the network based on the deviation in the solar adoption rates, and a lower deviation represents a more accurate network. The second phase of the analysis was a susceptible infected resistant model, which represented a dynamic analysis. So the SIR model is a model traditionally used to understand infectious diseases, as the name may imply. So this is used to understand how infectious diseases go from one place to another, how they transmit. But here we use this to understand the transmission of the social contagion for solar adoption. So the infection was really adoption influence starting from every county, and the key adaptation as compared to, say, a disease was a dynamic transmission rate. So unlike traditional SIR models, the transmission rate was not a global constant, because that would not be representative of a real-world scenario, because the strength of interactions differs on commuter flow. So this was really useful in understanding how strongly these networks were, these nodes were connected, and changing the transmission rate or the influence between these counties based on that commuter flow. So the probability of transmission was the base beta, which was the base probability of transmission times the edge weight divided by the max network weight for the whole network. So the edge weight gave how strong this connection was in comparison to the max network weight. So to discuss some results of this homogeneity analysis and the dynamic diffusion, these are the results for the network homogeneity. So the socioeconomic model exhibited a 20.9% improvement in homogeneity over the commuter model. So this is the commuter model with a 0.00535 standard deviation, whereas this was the socioeconomic model. Of course, a lower standard deviation represents a more accurate clustering. Interestingly, the state-level policies were actually the strongest in their homogenizing effects, which opens paths for future research, but also shows the importance of state policy in determining solar adoption within an area. But the socioeconomic peer clusters did accurately describe static patterns of adoption, at least as compared to the commuter network. But to ensure that these results were not just the result of random chance, we also used a null comparison against random models, and all of this is just to say that these the tuned models performed much better than the random models in all scenarios. Now going to the dynamic network analysis. So the commuter network was the only model to produce a strong, statistically significant positive correlation with real-world adoption rates, compared to the socioeconomic model, which had a negative correlation. The commuter model had a positive correlation with real-world adoption rates, after the SIR simulation. So this was the only model to produce a strong, statistically significant positive correlation. So to understand the dual role of the social contagion, we find that the commuter network is better at predicting the spread of social contagion. However, the socioeconomic network's importance is supported by the static analysis, where the clusters in the socioeconomic network had a 20.9% lower standard deviation. So, while homophily explains static clusters, its network topology is too insular. It perfectly models the intra-cluster consistency, but fails to transfer the novel influence across geographic voids. And that is where the commuter model comes in. To reconcile these models, then, we find that a dual mechanism solution is necessary because the commuter network predicts dynamic spread. So the social contagion actually does have two distinct mechanisms working at it. So the propagation occurs through the commuter network, which provides the necessary structural channels for information flow, while receptivity is based on homophily and acts as a filter for acceptance once the information actually arrives. And a lot of this is based on these findings are supported by the theory of the strength of weak ties. Granovetter 1973 provides a theoretical basis for our work. So commuter roots are the weak ties. They act as bridges between disparate communities, allowing the introduction of new ideas. But socioeconomic clusters form strong ties because these are high-cost, high-visibility innovations like solar panels require a risk reduction through peer validation. So strong ties convert this information flow into actual adoption because while the commuter routes represent bridges between communities that allow social proof to travel, it does not necessarily convert to adoption because there's a filter for acceptance through the socioeconomic peer similarity. But there are some limitations to this study because we use physical proxies, of course, namely the commuter model, as well as the nature of the data. So the ACS commuter data strictly maps physical travel again, not digital influence, which is increasingly important in our 21st century world. And the deep solar data does provide an aggregated snapshot. So this is not necessarily a longitudinal analysis of network topologies because instead we chose to use a dynamic model to actually predict and model that, but we did not have the data for it. So future work could look at more recent deep solar data releases and compare the network topology over time. So a temporal evolution could better understand the predictive accuracy of this model, as well as integrating social media and digital networks because they play an increasingly important role in the adoption and information flow idea. But what are the policy implications of this? So the effective campaigns need to tap into both mechanisms of the social contagion. They cannot just rely on one, which is often the case now. So by using broad channels, so commuter and mobility networks, to spread awareness, but then tailor the message and incentives to specific socioeconomic peer groups that will then ensure receptivity. So a hybrid campaign design must therefore be pursued where in phase one, we use high volume commuter corridors to maximize the broad diffusion of the awareness of the incentives themselves. But then when it comes time to disperse these incentives, we need to understand the socioeconomic peer groups in action and structure community engagement specifically targeted at these peer groups because our work shows that socioeconomic peer groups can increase receptivity of these new incentives and of the adoption of these new technologies because this would create a more robust boost for the solar panel industry and for incentives themselves because it would cause a more dual approach that works with both information flow as well as structural incentives. So to conclude, solar adoption does not spread through a single mechanism, and effective campaigns must target both socioeconomic peer groups and channels for information spread. So using both weak ties and strong ties, we can create a more targeted adoption campaigns that truly create a change. I would like to thank Dr. Daniel Casses at Cambridge University for his support throughout this project, especially in the conceptual basis for my network science results. And these are my references. Thank you so much for listening, and I really appreciate your time.